Trillions of times every second, you might be blinking out of existence and blinking back. Your body, your thoughts, the unbroken you reading this sentence. That is the claim, at least, and it comes not from mysticism, but from one of the most serious attempts physics has ever made to understand what space is actually made of. The theory is called loop quantum gravity, and its central idea, built on strange objects named spin networks, is that space is not a smooth stage that goes down forever. At the smallest scale imaginable, the Planck scale, space may come in indivisible grains, not a backdrop, but a fabric woven from quanta of geometry. And if space itself is granular, then smoothness, the very thing that makes you feel like one person flowing seamlessly through one unbroken life, may be only a large-scale appearance, a comfortable blur over something far stranger underneath. By the end, you will understand what a spin network really is, and why physicists say space has atoms, what that discreteness actually means, and why the dramatic headline that you flicker trillions of times a second is not quite what the equations say. Why the deepest equation of quantum gravity contains no time at all. And what all of this does, and does not, prove about the self, about freedom, and about whether anything continuous truly underlies you. Hold one question as we go. If the smoothness of space is only an appearance, then to whom does it appear? If you find value in explorations like this, in following the puzzles that keep physicists awake at night, consider subscribing to the channel, which helps these deep dives reach more curious minds. Now, let us begin. Begin with the floor beneath you. It feels solid, and it feels continuous. Between your chair and the floor, you assume, there is no smallest gap, no final tile of space that cannot be cut in half. Space, in ordinary experience, is a smooth and silent stage, infinitely divisible, the same all the way down, simply there, holding everything else. And you feel yourself to be just as continuous as the space you move through. One person, flowing without interruption from this moment to the next. The same self at the start of this sentence as at its end. These two assumptions, that space is smooth and that you are continuous, feel so obvious that naming them seems almost foolish. Yet the physics we are about to examine puts pressure on both, and it does so not with speculation, but with mathematics. The pressure comes from a problem physicists have wrestled with for nearly a century. We have two magnificent theories of the world, and they do not get along. General relativity describes gravity as the curvature of a smooth space-time, a flexible fabric bent by mass and energy. Quantum mechanics describes matter and the other forces as discrete, grainy, probabilistic, built from indivisible quanta and irreducible uncertainty. Each theory is among the most precisely tested in the history of science. But when you try to apply quantum rules to gravity itself, to ask what space-time is doing at the smallest scales, the mathematics breaks down. The smooth fabric and the grainy quantum refuse to be the same thing. To unite them is to answer a question general relativity never asks. What is space when you look closely enough to see its threads. Loop quantum gravity is one of the leading attempts to answer that question. It is not the only one, and it is important to be honest from the first minute. It is a candidate theory, not established physics. No experiment has yet confirmed it. But it is a serious, mathematically rigorous program, and its central move is bold. Most attempts to quantize gravity start by assuming a fixed, smooth background of space, and then adding small ripples of gravity on top, the way you might add waves to a calm pond. Loop quantum gravity refuses that picture. It is what physicists call background independent. It does not assume a pre-existing stage at all. Instead, it tries to quantize geometry itself, to treat the shape of space, its very fabric, as the thing that comes in quantum pieces. In a 2021 review, the physicists Abhay Ashtekar and Eugenio Bianchi described the central lesson of the program in a single phrase. Gravity is space-time geometry, and so geometry itself must be quantized. The stage, in this theory, is not the thing that holds the play. The stage is the play. To see how that could possibly work, we need to follow a thread of history, because the key idea was invented decades before the theory that now depends on it. In 1971, the mathematical physicist Roger Penrose, the same Penrose who would later win a Nobel Prize for his work on black holes, introduced a curious combinatorial object he called a spin network. At the time, it was a piece of pure mathematics, an attempt to build space out of nothing but discrete relationships and whole numbers, with no continuous geometry assumed underneath. It was elegant, and for years it was largely a curiosity. The machinery that would let it describe real gravity did not yet exist. That machinery arrived in 1986, when Abhay Ashtekar published a paper with the modest title New Variables for Classical and Quantum Gravity. Ashtekar found a way to rewrite Einstein's theory of gravity in a new mathematical language, one that looked much more like the gauge theories physicists already knew how to quantize, the theories that describe electromagnetism and the nuclear forces. In these new variables, the fundamental objects are not distances and curvatures directly, but quantities called connections, and their companions called fluxes, and, crucially, the holonomies of those connections, roughly the record of what happens to a quantum arrow when you carry it around a closed loop in space. Those loops are where the theory gets its name. 2 years later, in 1988, Carlo Rovelli and Smolin took Ashtekar's variables and built what is called the loop representation of quantum gravity in a paper titled Knot Theory and Quantum Gravity. The quantum states of space, they found, could be described by loops, and then by networks of loops. The decisive step came in 1995, when Rovelli and Smolin published Spin Networks and Quantum Gravity. They showed that Penrose's old combinatorial objects were exactly what the loop theory needed, a clean, mathematically well-behaved basis for the quantum states of geometry. And here is where we must slow down and picture what a spin network actually is, because everything else depends on it. Imagine a graph, a collection of points, which we will call nodes, connected by lines, which we will call links. This graph is not drawn in space. The graph is space, or rather, it is a quantum state of space, a single possible way for the fabric of geometry to be. Each link in the graph carries a label, a number drawn from the same family of values that labels quantum spin. 1/2, 1, 3/2, 2, and so on. That is why they are called spin networks. And each node, each junction where links meet, carries its own mathematical object called an intertwiner, which encodes how the spins of the meeting links are woven together. Think about that for a moment with care. Picture not a thing sitting in space, but a web of pure relationship, numbers on links, weavings at nodes, from which the appearance of space is meant to emerge. There is nothing underneath the graph. The graph is the bottom. Now comes the part that gives the theory its strangeness and its power. In loop quantum gravity, these graphs are not just bookkeeping, they are tied directly to geometry. The links of a spin network carry quanta of area. Whenever a surface is pierced by a link, that link contributes a specific, discrete amount of area to the surface. And the nodes carry quanta of volume. Each junction contributes a discrete chunk of volume to the region around it. Area and volume, the most basic measures of geometry, the things you would use a ruler and a measuring cup to find, are, in this theory, made of countable pieces. Rovelli put the point in a way worth quoting for its precision. These spin networks are not excitations in space, the way a sound wave is an excitation in air. They are excitations of space itself. The links and nodes are not objects located somewhere, they are the quanta of location. This leads to the single most striking and best established result inside the theory: the discreteness of geometry. In 1994, Rovelli and Smolin circulated a paper titled Discreteness of Area and Volume in Quantum Gravity, and over the following years, Ashtekar and Jerzy Lewandowski put the result on rigorous mathematical footing, with their area operator work appearing in 1996 and 1997, and their volume operator work following close behind. What they found is that the mathematical operator representing area, quantum mechanical question, how much area is here, does not have a smooth, continuous range of possible answers. It has a discrete spectrum. The area of a surface, in this theory, cannot take just any value. It can only take certain specific values, separated by gaps, in the same way that the energy of an electron in an atom can only take certain specific levels and nothing in between. There is an equation for this, and it is the flagship formula of the whole program, so let us state it carefully. The area of a surface, call it A, is given by A equals 8 pi gamma times the Planck length squared times the sum over all the links that pierce the surface of the square root of j times the quantity j plus 1. In symbols, A equals 8 pi gamma L-P squared times the sum of the square root of j minus I times j minus I plus 1. Let us take it apart. The quantities j are the spin labels on the links that pierce the surface, those half integers, 1/2, 1, 3/2. The square root term, the square root of j times j plus 1, is the same expression that appears throughout quantum mechanics whenever spin is involved. It sets how much area each pierce contributes. The symbol gamma is a number called the Barbero-Immirzi parameter, named for the physicists Fernando Barbero and Giorgio Immirzi. It is a kind of conversion factor, a free constant that scales the whole spectrum, and we will meet it again when we reach black holes. And L-P is the Planck length, the natural unit of length at which gravity and the quantum meet. The entire message of the equation is in its structure. Area is a sum of discrete contributions, each one a square root multiple of a fundamental unit. You cannot have a little less than the smallest pierce. There is a smallest non-zero patch of area the theory allows, and below it there is no less area. There is nothing. How small is that fundamental scale? This is where the numbers become almost meaningless to the human imagination, and we should state them exactly rather than wave at them. The Planck length is built from 3 of the deepest constants in physics: Newton's gravitational constant, g, the speed of light, c, and the reduced Planck constant, h bar, combined in a single expression. L-P equals the square root of h bar g over c cubed. Plug in the measured values and you get a length of 1.616 times 10 to the minus 35th meters. To feel how small that is, it is about 6.4 times 10 to the minus 34th inches, a decimal point followed by 33 zeros and then a 6 before you reach any meaningful digit. An atom is already 100 millionth of a centimetre across, and the Planck length is smaller than an atom by roughly the same factor that an atom is smaller than the solar system, and then smaller still. The companion Planck time, the time it takes light to cross that length, is 5.39 times 10 to the minus 44th seconds. The Planck area, the length squared, is about 2.6 times 10 to the minus 70th square meters. These are not round numbers chosen for drama. They are the scale at which this theory proposes the smooth continuum of space should give way to grain. What does it mean that the most basic features of the world, a patch of area, a pocket of volume, might be built from countable units, the way matter is built from atoms? At minimum, it means the smoothness we take for granted could be like the smoothness of a photograph in a newspaper, continuous to the naked eye, but resolving under a magnifying glass into a field of separate dots. Run your finger across this page and it feels unbroken. The discreteness is real, but hidden far below the scale of your senses. Loop quantum gravity proposes that space is like that, seamless at every scale you will ever touch, and grainy only at a depth no instrument has ever reached. It is worth pausing on how genuinely strange this result is, because familiarity can dull it. We are used to the idea that matter is made of atoms. That was strange once, and now it is ordinary. But the claim here is not about the stuff inside space. It is about space, the container, not the contents. The theory says that the very arena in which how much room is there is asked has a smallest possible answer. Stranger still, the quantities that come out cleanly in the theory are area and volume, while length, the simplest measure of all, the thing a ruler reads, turns out to be far more awkward and less fundamental, almost an afterthought. That is the reverse of everyone's intuition, in which length comes first and area is length times length. In loop quantum gravity, the graph of relationships comes first, and your ruler is a derived, blurry, large-scale convenience. It is worth lingering on Ashtekar's variables because they are where the loops in loop quantum gravity come from, and the idea is more concrete than it first sounds. Einstein's gravity is ordinarily written in the language of distances and curvature, the metric, the field that tells you how far apart things are. Ashtekar's reformulation trades that language for one borrowed from the theories of the other forces. A connection, the mathematical object that tells a quantum arrow how to turn as it is carried from place to place. And its partner, a flux associated with surfaces. The key quantity built from the connection is the holonomy, the record of how much a quantum arrow has been rotated after you carry it all the way around a closed loop and back to where it began. On a curved geometry, an arrow carried around a loop returns pointing in a different direction. The holonomy captures exactly that twist. Those loops are not metaphors. They are the literal closed paths whose holonomies became the first variables of the quantum theory. And when Rovelli and Smolin found that the quantum states could be labelled by networks of such loops, the loops gave the whole program its name. The lesson to carry forward is that the fundamental description is not built from points and distances at all. It is built from relationships. What happens around loops, how arrows turn, how surfaces are threaded. The nodes of a spin network deserve the same care, because they carry the quantity that is hardest to picture and most intimate to the self: volume. Each junction where links meet holds a mathematical object called an intertwiner, and the intertwiner is best understood as the rule for how the spins of the meeting links are woven together at that point. It is the knot at the crossing. And it is the intertwiner that fixes how much volume the theory assigns to the little region around that node. So the picture sharpens. The links of the network, threading through surfaces, supply the quanta of area. The nodes, with their woven intertwiners, supply the quanta of volume. A region of space contains a definite amount of volume precisely because it contains a definite number of nodes, woven in definite ways. Empty the region of nodes, and you have not emptied a container. You have removed the volume itself. There is no leftover room. The nodes are the room. This is the place to notice one of the theory's most disorienting reversals, the kind of thing that tells you you have left ordinary intuition behind. In everyday life, length is the simplest measure. You reach for a ruler first, and you build area and volume out of it by multiplying lengths together. In loop quantum gravity, the order is upside down. Area and volume are the clean, fundamental, beautifully behaved quantities, each with its own well-defined operator and its own discrete spectrum. Length is the awkward one, harder to define, less central, more troublesome to turn into a respectable operator at all. Rovelli, considering the difficulty, admitted with disarming honesty that he was not sure whether the trouble with length was a mere technical nuisance or a sign of something deeper. Sit with how strange that is. The measure you trust most, the one your hands and eyes are built around, is in this theory the derived afterthought. And the measures you rarely think about, area and volume, are the bedrock. It is a vivid reminder that the smooth, ruler-friendly space of daily life is not the foundation, but the surface, a large-scale convenience laid over a structure that does not share our priorities. These graphs were not only elegant, they could be made to solve the theory's central equation, and early on. In 1988, in a paper titled Non-Perturbative Quantum Geometries, Ted Jacobson and Lee Smolin found some of the first exact solutions of the Hamiltonian constraint, actual quantum states of geometry that satisfied the demanding central equation of the theory, written in the loop language. It was an early sign that the program was not merely suggestive, but tractable, that you could write down honest solutions and not only gesture at them. Jacobson's contributions to this early period and to quantum gravity more broadly are substantial and widely cited. Popular accounts sometimes promote him to an outright co-creator of loop quantum gravity. The careful historical record is more measured, and where a confident title is wanted, it is the kind of claim a responsible account flags rather than asserts. The point that survives any quibble over credit is the result itself. By the late 1980s, the loop description was not a sketch. It was working machinery with exact solutions in hand. What does it mean that the deepest description of space prefers area and volume to length, and relationships to points? That it is built from how arrows turn around loops rather than from how far apart things sit? At minimum, it means the intuitions we are about to lean on when we ask grand questions about the self were shaped by the surface, not the depths. The space that feels so plainly smooth, so obviously continuous, so evidently the simple backdrop to your one unbroken life is, if this theory is right, none of those things at the bottom. And a mind reaching confident conclusions about identity from the felt smoothness of the world is reaching them from exactly the layer the physics says is only an appearance. These ideas did not stay purely abstract. The theory found at least one concrete point of contact with known physics, and it is worth marking because it is one of the few places where loop quantum gravity touches a result everyone already accepts. In the 1970s, Jacob Bekenstein and Stephen Hawking discovered something profound about black holes. A black hole has an entropy, a measure of hidden information, and that entropy is proportional not to the black hole's volume, as you might expect for ordinary stuff, but to the area of its horizon. The formula, the Bekenstein-Hawking entropy, says the entropy, S, equals Boltzmann's constant times the area, divided by 4 times the Planck length squared. Notice the Planck area sitting in that denominator. Black hole entropy is, in effect, counted in Planck area units. In 1996, Carlo Rovelli showed that loop quantum gravity could reproduce this relationship by literally counting the spin network states that thread the horizon, the discrete quanta of area piercing the black hole's surface. Ashtekar, John Baez, Alejandro Corici, and Kirill Krasnov developed the calculation further in work published in 1997 and 1998. The match works, but it comes with a catch we will need later. It only comes out exactly right for a particular value of that free parameter gamma, the Barbero-Imirzi number. The theory does not predict gamma from first principles. It is tuned to fit. Hold that thought. We will return to it. Let us lay the historical sequence out plainly, because the dates matter and the names will recur. In 1971, Penrose introduces spin networks. In 1986, Ashtekar introduces his new variables. In 1988, Rovelli and Smolin build the loop representation, and in the same year, Ted Jacobson and Lee Smolin find some of the first exact loop state solutions of the theory's central equation. In 1994, the discreteness of area and volume is announced. In 1995, spin networks become the official basis. In 1996 and 1997, the area and volume operators are made rigorous. In 1996, black hole entropy is derived from the counting of quanta. These are the load-bearing beams of the structure. Around them, popular accounts sometimes call various early contributors co-creators of the theory. The historical credit is real, though the exact labels are worth holding loosely. And I will flag where a confident claim outruns the careful record. So this is the picture Part 1 leaves us with, presented as neutrally as the physics demands. There is a serious, rigorous, still unconfirmed theory in which space is not a smooth and bottomless stage, but a web of discrete relationships, spin networks, whose links carry quanta of area and whose nodes carry quanta of volume. Geometry in this theory is granular at the Planck scale, a scale so small it has never been probed and may never be directly seen. The result is mathematically among the strongest the program has produced, and it touches reality at one point: the entropy of black holes. We have not yet asked what any of it means for time, which behaves even more strangely than space. We have not yet tested the dramatic claim in our title, that you, the continuous self, flicker in and out trillions of times a second. And we have planted 2 seeds we must return to, that this discreteness is a discreteness of the mathematical spectrum, which may be subtler than a literal grid of pixels, and that the theory's neat results lean on a number, gamma, that had to be chosen rather than derived. Keep both in mind. For now, we turn from space to time, and to the equation at the heart of quantum gravity, in which time does not appear at all. A spin network, we said, is a quantum state of space, a single frozen snapshot of geometry, one possible way for the fabric to be at one instant. But physics is not made of snapshots. Things happen. Geometry changes. A theory of space that could not describe how space evolves would be only half a theory. So we must ask how loop quantum gravity handles change. And the answer introduces the second of its two central objects. And it is here that the picture becomes genuinely subtle. The objects that describe evolution are called spin foams. If a spin network is a graph, nodes and links representing a slice of space, then a spin foam is what you get when that graph is allowed to evolve. The nodes sweep out lines, the links sweep out surfaces, and the whole thing becomes a kind of higher dimensional scaffolding, a structure of faces and edges and vertices that connects one spin network to another. The physicist Alejandro Perez, whose 2013 review is the standard reference, describes a spin foam as the covariant path integral side of the theory, a sum over the possible quantum histories of geometry, each history weighted by an amplitude. In the cleanest formulation, the total amplitude is written as a sum over all foams, with each foam contributing a product of amplitudes assigned to its faces, its edges, and its vertices. In words rather than symbols, the probability of getting from one shape of space to another is computed by adding up the contributions of every quantum geometry that interpolates between them. It is tempting, and almost every popular account makes this mistake, to imagine a spin foam as a film, frame after frame of the universe, the cosmos blinking forward one Planck tick at a time, like the frames of a movie reel. Resist that image because it is wrong, and the way in which it is wrong is the key to this entire episode. A spin foam is not a sequence of universal moments laid end to end. It is a transition amplitude between boundary states, a mathematical structure that connects an initial configuration of space to a final one, summed over all the ways in between. There is no master clock ticking off the frames. There is no privileged now sweeping through the foam. The safest way to say it, and the way Perez's careful language supports, is this. Spin networks are states of space on a boundary. Spin foams are the histories or amplitudes that connect those boundaries. The movie metaphor smuggles in exactly the thing the theory most conspicuously lacks: a universal time. And that absence is not a minor technicality. It is, in canonical quantum gravity, the deepest puzzle of all. That puzzle has a name: the problem of time. To understand it, recall how ordinary quantum mechanics works. You have a system, and you have a background clock, an external time, t. And the system evolves with respect to that clock. The equation that governs it, the Schrödinger equation, literally has time in it. It tells you how the quantum state changes from one moment to the next. Time is the stage on which the quantum drama plays out. But general relativity taught us that time is not an external stage. Time is part of space-time, part of the very geometry that gravity bends. So when you try to write down the fundamental quantum equation for geometry itself, the equation that should govern the wave function of the entire universe, there is no external clock left to evolve against. Time cannot be the background, because time is part of the thing being quantized. The result is one of the strangest equations in physics. It was first written down in the 1960s, growing out of the work of John Wheeler and Wheeler-DeWitt, whose 1967 paper is its origin, and it is called the Wheeler-DeWitt equation. In its compact form, it reads h hat psi equals 0. That is the whole thing. H hat is the Hamiltonian constraint, the operator that, in an ordinary theory, would generate evolution in time. Psi is the wave function of the universe, the quantum state of all of geometry and matter at once. And the right-hand side is 0. In a normal quantum theory, the Hamiltonian acting on the state tells you how the state changes in time. Here, the Hamiltonian acting on the state of the universe gives you nothing, gives you 0. There is no leftover time derivative, no "and then it evolves." The fundamental equation of quantum gravity describes a universe that does not, in any external sense, evolve at all. Physicists call it the frozen formalism. The deepest equation we can write for the cosmos appears to describe something timeless. Now you must hear very carefully what that does and does not mean, because this is precisely the kind of statement that gets stretched past its evidence. Time is absent from the fundamental equation is not the same as nothing ever happens. Things plainly happen. You are watching this. The seconds are passing. Change is the most obvious fact of experience. What the frozen formalism says is narrower and stranger, that the familiar external time parameter has dropped out of the deepest description, and that the experience of time and change must be recovered in some other way, relationally, by tracking how one part of the universe changes with respect to another, or smoothness, in the limit where the world looks laugh by the shape of the quantum may be the cart in well, or smoothness, in the limit where the friends of the part of the time well. Maybe the cart of the state provide yonder, in the limit where the friend's desire happens, in the limit where the deepest description for the deepest changes. What the frozen formalism says is narrower by tracking how one part of the universe change is relationally. Maybe the cart in the time and change must be recovered in some. And that the limit where the world looks classical, or through those transition amplitudes the spin foams encode. In Ashtekar's words, writing about quantum cosmology, there is no external time to phrase questions about evolution. Time in this picture is not a given. It is something that has to emerge, a relationship between things, not a container holding them. One common move is to let a particular field of matter serve as a relational clock. The universe does not evolve in time, but you can ask how everything else looks when this chosen field has this value, and that recovers something like the flow we experience. Hold that distinction with both hands. Time absent from the equation versus nothing changing. because it is the single most abused idea in this whole subject, and we will return to those who abuse it. Now we are equipped to test the dramatic claim in our title head-on, and honesty requires that we do, even though the claim is the reason the topic is so gripping. The headline says, "You disappear, or flicker, trillions of times a second." Where would such a number come from? The natural guess is the Planck time, that fundamental tick of 5.39 times 10 to the minus 44th seconds. If you imagine the universe updating itself once per Planck time, like a cosmic frame rate, how fast would it flicker? A trillion times a second is 10 to the 12th. The reciprocal of the Planck time, 1 divided by that tiny number, is about 1.85 times 10 to the 43rd per second. Set them side by side. 10 to the 12th against 10 to the 43rd. The true figure is not trillions. It is larger than a trillion by a factor of 10 to the 31st. That is, by 10,000 billion times. Trillions per second undersells the naive number by 31 orders of magnitude, which is a way of saying it is not even in the right universe. But the deeper problem is not that the number is too small. It is that the number should not be computed at all, because the theory does not license it. Loop quantum gravity does not assert a universal Planck rate clock ticking everywhere in unison. It does not say that macroscopic persons blink out of existence and back at any rate. Not trillions per second, not 10 to the 43 per second, not any rate. Remember the problem of time. There is no master clock to tick. And remember what the discreteness actually is. A discreteness in the spectrum of geometric operators, in the possible answers to how much area is here. Not a literal strode light flashing the cosmos on and off. So the honest framing, the one a careful physicist would give, is this. If you naively turned the Planck time into a universal frame rate, you would get something like 10 to the 43rd per second, not trillions. But canonical quantum gravity does not endorse that naive picture in the first place. The flicker is not too fast. The flicker, as a literal cosmic strobe, is not there. This brings us to the second seed we planted, and it deserves its own careful treatment, because it corrects the most popular image of the whole theory. When people hear space is discrete, they picture a grid, a three-dimensional graph paper lattice, tiny cubes of space stacked like bricks. A literal pixelation of reality with hard edges at the Planck scale. That image is wrong, and the reason it is wrong is a principle at the very heart of general relativity called diffeomorphism invariance. It means, roughly, that the location of the graph in space carries no physical meaning. If you take a spin network and slide it, stretch it, deform its embedding, move the nodes around without cutting any links, you have not produced a different physical state. You have produced the same physical state, described differently. In the theory, the physical states are not the embedded graphs themselves, but equivalence classes of them, whole families of deformed pictures, all counted as one. There is no fixed lattice pinned to fixed points of space, because points of space in that absolute sense do not exist. What is discrete is the relational structure, how many links, what spins, how they connect, and the spectra of the operators built from it. What is not discrete is a literal pixel grid you could, in principle, photograph. The graininess is in the relationships, not in a cosmic checkerboard. The diagram to keep in mind is not graph paper. It is a knot. What matters is how it is tied, not where on the table it sits. What does it mean that the most arresting popular images of this theory, the cosmic film reel, the pixelated space, the strobing self, are precisely the parts the physics does not support? It means we are in the presence of a genuine and disciplined strangeness that is being routinely traded for a cheaper, false one. The real theory is stranger than the cartoon, and more careful. And keeping the real one in view is exactly what will matter when we reach the claims people build on top of it. Loop quantum gravity does make one prediction vivid enough to picture, though even here we must be careful about which version of the theory is talking. Apply the loop techniques not to the whole universe, but to a simplified, symmetric model of an expanding cosmos, and you get a subfield called loop quantum cosmology. It is important to be precise. Loop quantum cosmology is a symmetry-reduced approximation, not the full theory, and results proven there do not automatically hold in general. But within that model, something striking happens to the beginning of the universe. In standard general relativity, if you run cosmic expansion backward, everything converges to a single point of infinite density, the Big Bang singularity, where the equations break down and physics ends. Loop quantum cosmology replaces that catastrophe with something else. Its effective equation modifies the standard cosmological law with a single correction term. The rate of expansion squared, h squared, equals the usual 8 pi g times the density over 3, but now multiplied by the factor 1 minus the density divided by a critical density. In symbols, h squared equals 8 pi g rho over 3 times the quantity 1 minus rho over rho critical. Read what that correction does. As the density climbs toward the critical value, the term in parentheses falls towards 0, and the expansion rate is forced to vanish. The universe stops collapsing and rebounds. The singularity is replaced by a bounce. The Big Bang becomes, in this model, a big bounce, a transition from a previous contracting universe to our expanding one. The work establishing this by Ashtekar, Tomasz Pawlowski and Parampreet Singh appeared in 2006. The numbers attached to the bounce carry a lesson worth stating, because they puncture another misconception, that quantum gravity is something that only happens when the universe is unimaginably tiny. The critical density at which the bounce occurs is about 0.41 times the Planck density, an enormous density, but a density, not a size. Ashtekar's review gives a concrete example. A model universe that grows to a maximum radius of a megaparsec, millions of light years across, undergoes its quantum bounce at a minimum volume of about 5.7 times 10 to the 16th cubic centimeters, which is roughly 5.7 times 10 to the 10th cubic meters, or on the order of 2 trillion cubic feet. That is not a pinpoint. It is a sizable volume. The trigger for quantum gravity, the example teaches, is not that the universe is small, but that it is dense, that the curvature, the concentration of energy reaches the Planckian regime. And the same review notes the reassuring flip side. Once the density falls below roughly 1% of the Planck density, ordinary general relativity is already an excellent approximation, and the quantum repulsion fades away fast. Quantum gravity is not lurking in your living room. It is confined to the most extreme conditions the cosmos has ever known. Could we ever test any of this? The honest answer is that direct tests are hopeless. The Planck scale is so far beyond any conceivable instrument that physicists must look for indirect echoes. The most discussed echo concerns a deep question. If space has a smallest scale, does that smallest scale break one of the sacred symmetries of physics, the Lorentz invariance, that guarantees the laws look the same to all observers moving at constant velocity, and that nothing outruns light? Some models of Planck scale discreteness predict that very high energy light should travel at a slightly different speed than low energy light, that the granularity of space should, over enormous distances, smear a flash of light by energy. So astronomers watch the most distant, most violent flashes in the cosmos. Gamma-ray bursts, billions of light-years away. In 2009, the Fermi Gamma-Ray Space Telescope observed a burst called GRB 090510 and found no sign of the predicted energy-dependent delay. The high-energy and low-energy photons arrived together, setting a bound that pushed the simplest such effects beyond the Planck energy itself. A later analysis tightened the limit further still. In 2011, observations of another burst, GRB 041219A, by the Integral satellite, used the polarization of its light to place extremely tight constraints on a related effect called vacuum birefringence. These are real, important results. But here too, precision matters. They constrain certain specific Lorentz-violating effective models. They do not test loop quantum gravity as a whole, because the discreteness in loop quantum gravity is relational and does not obviously single out a preferred frame at all. The experiments rule out some ways space might be grainy. They leave the careful version untouched and unconfirmed. It is worth slowing down on how a timeless theory recovers the time we live in, because this is where the frozen formalism stops sounding like a paradox and starts sounding like a discipline. The idea is called relational time, and it is older and simpler than the equations. Imagine you have no external clock, none at all, but you have a pendulum and a candle. You cannot ask in absolute terms what time it is, but you can perfectly well ask how far the candle has burned by the time the pendulum has swung 1,000 times. You have replaced absolute time with a relationship between two changing things, and nothing is lost. Every question you wanted to ask about when becomes a question about how this looks when that has reached such and such a value. Canonical quantum gravity does the same thing on a cosmic scale. There is no external clock for the universe, so you choose something inside it, often a field of matter, a quantity that changes steadily, and you let it serve as the clock. You do not ask how the universe evolves in time. You ask how everything else in the universe looks when the chosen field has this value, and then the next, and then the next. Out of that relational bookkeeping, the familiar river of time re-emerges, not as a fundamental given, but as a pattern in how the parts of the world keep pace with one another. There is a second route back to time, and it matters because it is the one your everyday life rides on. The large and smooth and tame, which is to say, everywhere you have ever been. The quantum equations settle into a regime where one variable behaves so steadily and so universally that it can act as an excellent approximate clock for everything else. And the timeless deep description gives way to the ordinary flowing time of physics as usual. The timelessness is real at the foundation and invisible at the surface, in exactly the way the graininess of space is real at the Planck scale and invisible to your hand on the floor. This is the pattern of the whole theory, stated once more. A strange, discrete, timeless bottom and a smooth, flowing, continuous top. With the top, emerging from the bottom by coarse graining and good approximation. You live on the top. You were built on the top. Your intuitions are intuitions of the top. Keep that firmly in view because it disciplines what we are allowed to conclude. The frozen equation, h hat psi equals 0, is a statement about the foundation, about the wave function of the entire universe, an object so far from daily experience that it has no clock of its own. It is not a statement that your afternoon has no order, that your deciding has no reality, that your before and after is a fiction. Those are claims about the top, and the top is precisely where time, relational and emergent and entirely real to those who live in it, has come back. To take a fact about the timeless foundation and apply it, unmodified, to the lived surface is to commit, in time, the very same error the pixel grid image committed in space. It mistakes the deep description for the everyday one, and then it draws human conclusions from the wrong floor. What does it mean that the universe might have no clock of its own, and yet be filled, top to bottom, with creatures who cannot stop experiencing time? It means at least this, that the flow of time, like the smoothness of space, may be a feature of the surface we inhabit rather than of the foundation we are made from, and that the surface, with its real change, its real mornings, its real one-way memory, is not thereby an illusion. It is the layer where we live, lawfully produced by the layer beneath. The river is real even if it rises from a still and timeless spring. And a still, timeless spring, from which all change flows, is, once again, an idea far more familiar to theology than to the popular science that fears it. And loop quantum gravity is not alone in the field. It is one of several serious, competing programs, each making different bets about what lies beneath space-time. String theory proposes that the fundamental objects are not points, but tiny, vibrating strings, and that gravity emerges, unified with the other forces, in a framework that typically requires extra dimensions. Causal set theory proposes that space-time is, at bottom, a discrete set of events ordered only by cause and effect, discreteness and causality taken as primitive. Causal dynamical triangulations build space-time from a path integral over tiny triangulated building blocks, glued together with a strict causal rule. None of these has achieved decisive experimental confirmation. None can yet claim victory. The fair way to describe the landscape is not loop quantum gravity versus the truth, but several serious attempts at a problem that remains genuinely unsolved. That humility is not a weakness in the science. It is the science being honest about where it stands. It is worth being concrete about where the science actually stands, because the gap between what is established and what is merely hoped for is exactly the gap the loose claims will try to leap. What is known with relative confidence inside the framework is real and not small. The kinematical structure, the space of quantum states, can be built rigorously. The spin network techniques do make the geometric spectra discrete, and the cosmological model produces its bounce robustly in simple cases. What remains genuinely open is just as real. The full dynamics, governed by that Hamiltonian constraint, is not settled. The recovery of the smooth classical world we actually see has not been fully derived. The exact relationship between the full theory and its cosmological shadow is debated, and the coarse graining of the spin-foam sum is an unsolved problem. And the verdict that matters most is the simplest one. No experiment yet selects loop quantum gravity over its rivals. That is the true shape of the knowledge, a solid island of internal mathematics ringed by open water. What does it mean that a theory can be this rigorous, this internally coherent, this beautiful, and still be entirely unconfirmed by nature? It means that beauty is not evidence, that rigor is not proof, and that anyone who treats this elegant island as though it were the whole map has quietly stopped doing science and started to preach. So, part 2 deepens the picture, and in doing so, quietly dismantles the cartoons. Spin foams describe the histories of geometry, but they are not a film, and there is no master clock. The Wheeler-DeWitt equation removes time from the deepest description. But timelessness in the equation is not the same as a frozen, changeless world. The headline flicker, trillions or any number per second, is both numerically wrong and conceptually unlicensed. The discreteness is spectral and relational, not a literal lattice you could photograph. The one vivid prediction, the cosmic bounce, lives in a simplified model and is triggered by density, not by size. And the theory remains, by the testimony of its own architects, unconfirmed, one candidate among several. Through all of it runs a pattern we are now ready to name. At every turn, a precise and modest physical statement has a grander, looser claim hovering just above it, waiting to be mistaken for it. Space is grainy at the Planck scale. Therefore, the loose version whispers, "You are not really continuous, not really one self, not really persisting, and perhaps nothing continuous underlies you at all." We have reached the place where the physics ends and the interpretation begins. In the final part of this exploration, we stop presenting and start examining. We ask what these beautiful, unconfirmed equations actually prove about you, and what they cannot. For 2 parts, I have presented and not prosecuted. I laid out loop quantum gravity as fairly as I could. The spin networks that recast space as a web of discrete relationships. The area and volume operators with their discrete spectra. The Planck scale graininess. The spin foams. The frozen Wheeler-DeWitt equation. The cosmic bounce. I corrected the cartoons where honesty required, the film reel, the pixel grid, the strobing self. But I debunked no one's worldview. That was deliberate. Now we examine. Now we ask what these elegant, unconfirmed equations actually establish about you, and where the established physics ends and something else begins to wear its clothing. Let me state the spine of this final part as plainly as I can, because everything hangs on it, and because, remarkably, it is not my invention. It is written into the research literature itself. There is what loop quantum gravity at most suggests, that the geometry of space may be granular at a scale no instrument has reached, in a theory no experiment has confirmed. And there is what is repeatedly bolted on top, that you, therefore, have no continuous self, that time is unreal, that freedom is an illusion, that the early universe explains itself, that mind is merely matter, that there is no soul and no God. The careful summary, the one that honest physicists give, is that this second list does not follow from the first. The claims about a discrete self, the non-existence of God, the falsity of the soul, these are not results of the theory. They are philosophical additions, and they must be examined as such, not smuggled in wearing a physicist's coat. Take the first and most seductive claim, the one our title dangles, that discrete or timeless physics proves the self is an illusion, that you are nothing but a flickering pattern, a sequence of disconnected stages with no continuous thread, no real you persisting from one instant to the next. Give it its strongest form. Pair the granularity of space with the timeless equation and the philosophical tradition that already doubts the enduring self, the view that persons are just temporal stages or chains of psychological continuity with no deep further fact binding them, And you get a picture in which you is a convenient fiction the brain narrates over a stuttering, discontinuous substrate. It is a vivid picture. It has moved serious people. Now let us examine it. Begin with what loop quantum gravity actually says, because the claim leans on the word discrete, doing far more work than the physics permits. We established it in part 2, and it bears repeating as the hinge of the whole argument. The discreteness in this theory is a discreteness in the spectrum of geometric operators, in the possible answers to how much area is here. It is not a strobe light flashing the cosmos on and off. There is no master clock. The deepest equation has no external time to tick. So the image of you blinking out and back trillions of times a second is not a daring extrapolation of the theory. It is a misreading of it. The theory does not contain that strobe. And notice who confirms the caution. Even the question of whether time itself is discrete remains unproven. The researchers Marios Christodoulou and colleagues, examining exactly this, wrote that discreteness of time may arise in the formalism, and then added, in the same breath, that nothing has been proven yet. The flicker is not a result, it is not even a settled conjecture. It is a headline. But suppose we grant the granularity completely. Suppose space really is a web of quanta, and your body really is, at the Planck scale, a pattern over a discrete geometry. Does it follow that the self is an illusion? Trace the inference because there is none. Loop quantum gravity quantizes geometry. It says nothing whatsoever about the conditions for personhood, for selfhood, for the unity of a conscious life. Personal identity is a distinct question, a philosophical one, untouched by the spectrum of an area operator. To move from the area operator has discrete eigenvalues to there is no continuous you is not a deduction. It is a leap across a chasm with nothing but rhetoric for a bridge. The physics underdetermines the metaphysics. The same granular geometry is perfectly compatible with an enduring self, with a soul, with a continuous I. The equations simply do not address the matter. To claim otherwise is to mistake a statement about rulers for a statement about the one who reads them. And here the examination becomes a question the materialist cannot answer, and it is the keystone of this entire episode. Return to the question I asked you to hold from the very first minute. If the smoothness of space is only an appearance, then to whom does it appear? An appearance is not free-floating. An illusion is not a fact about the world alone. It is a fact about how the world seems to a subject. The granularity of space, even if it is real, is presented to someone, gathered into a single, seamless experience by a unified awareness that takes the trillion separate quanta and knows them as one smooth floor, one continuous room, one unbroken moment of being alive. Slice space into its finest grains, and you have described the stage in exquisite detail. You have said nothing at all about the one for whom the stage is a world. The spin network explains the geometry. It does not explain the geometer. This is the consciousness argument, and on this topic it cuts to the bone, because the theory's own granularity sharpens it rather than dissolving it. Grant that you are a pattern over a discrete geometry. You must now explain not merely how unconscious matter becomes a mind, which no physical theory has done, that is the famous hard problem, unsolved by the admission of those who work on it, but how a pattern strung across a discontinuous, clockless, quantum substrate becomes one continuous experiencer who binds the grains into a single life and is aware that it is doing so. No quantum of area is conscious. No link, no node, no intertwiner is aware. The relations between them are not aware. And yet, here is the datum more certain to you than any equation. There is one of you, now, gathering these words into a single understanding. Where, in a web of unconscious quanta, did the one who gathers them come from? The discreteness does not answer this. It makes the question louder. Hear, finally, how the claim consumes itself, because the deflationary move has a reductio inside it. To say the self is an illusion is to say that a self is being deceived, that there appears to be a continuous I where there is none. But an illusion requires a subject to suffer it. If there is genuinely no continuous self, then there is no one for the illusion to fool, no one to whom the false smoothness seems smooth. The self is an illusion can only be asserted by the very self it denies. It saws off the branch on which it sits. What does it mean that every attempt to dissolve the self must be carried out by the self it is trying to dissolve? It means we have struck something that does not reduce. The unified, conscious I, the one continuous thing in this entire account of a discontinuous world. The granularity of space leaves it not weakened but isolated, standing alone as the one feature no arrangement of unconscious quanta can manufacture. And a thing that cannot be built from the parts is exactly the kind of thing that must be given, by a cause that is itself conscious and itself one. Turn to the second claim, the one that follows the timeless equation into the human heart. That if time vanishes from the fundamental description, then freedom and moral agency vanish with it. That a frozen universe is a universe with no genuine choices, no real becoming, nothing but a fixed block in which your sense of deciding is a trick. Give it its strongest hearing. The Wheeler-DeWitt equation really does read h hat psi equals 0, with no time on either side, and that is a startling thing. Now examine the leap. We did the decisive work already in part 2. Time being absent from the equation is not the same as nothing happening. The familiar external clock drops out of the deepest description, but change is recovered relationally, by how one part of the world stands to another, and the experience of flow re-emerges in the world we actually inhabit. So the argument, no time in the equation, therefore no real becoming, therefore no freedom, rests on conflating two utterly different statements, And the conflation is the whole trick. Strip it out, and the physics says only that time is relational and emergent, not that agency is an illusion. The philosophy of free will is a genuine and unsettled debate, with compatibilist and incompatibilist and fatalist positions all on the table. An equation without an external time parameter does not reach in and settle that debate. To think it does is a category mistake, answering a question about moral responsibility with a fact about a Hamiltonian constraint. Press the point with a reductio the fatalist cannot escape. Suppose the argument is right and there is no real change, no genuine before and after, only a frozen block we mislabel with the language of flow. Notice what you just did to consider that claim. You held the premises in mind, and then you moved to the conclusion. A real transition, a real change in your understanding, from not seeing the point to seeing it. Reasoning is itself a temporal act, a becoming. An argument whose conclusion is there is no real becoming must be followed through a real becoming in order to be believed. It refutes itself in the act of being thought. The lived reality of change is not a stray illusion to be explained away. It is the precondition of explaining anything at all. And there is an inversion waiting here that the skeptic never expects. Suppose, for the sake of argument, that the deepest description of reality really is timeless, that beneath the flow of moments lies a single, eternal, lawful totality. Notice what that is. It is not a picture that banishes a creator. It is the picture classical theism drew of one, long before any physicist wrote h hat psi equals 0. An eternal reality, not strung out in time, but whole, beheld all at once by a cause that is itself outside time. A timeless, ordered, law-governed totality does not explain itself. It does not get to be both perfectly ordered and uncaused. The skeptic reaches for the frozen equation to crush human freedom into illusion, and in the same motion sketches a cosmos whose timeless, lawful order points past itself to a timeless lawgiver. The argument meant to retire eternity instead describes the throne of it. The third claim is the boldest, that quantum gravity removes the need for God because it explains the beginning. The Big Bang singularity, the point where the equations broke and a creator seemed to many to be required, is replaced in loop quantum cosmology by a bounce. No singularity, no absolute beginning, no edge where you must invoke something beyond physics. The universe on this telling is self-contained. It bounced from a previous phase. It needs no first cause. It explains itself. State it at full strength because it is the claim that launched 1,000 headlines. Now examine it with care and watch it come apart in 3 places. First, the modesty the physics demands. Loop quantum gravity is unconfirmed. Loop quantum cosmology is a symmetry-reduced model, a simplified toy, not the full theory. And its bounce is a result inside an approximation, not a measured fact about our past. To rest, there is no need for God on an unconfirmed result in a simplified model is to build a cathedral of metaphysics on a scaffold the builders themselves call provisional. By the testimony of its own architects, this is a candidate, not a conclusion. Second, and more deeply, even a complete, confirmed account of the early universe would not be what the claim pretends. Grant the bounce. Grant an eternal series of bounces, if you like, a cosmos with no first moment at all. You have described a mechanism, a process governed by precise mathematical laws, populated by specific physical constants, unfolding according to an exact and rigid structure. You have not explained why there are those laws rather than others, why those constants, why any lawful mathematical reality exists to bounce in the first place. A bouncing universe is still a contingent thing, still leaning on a framework it did not author. Removing the first moment does not remove the question. It only moves the question from what started it to why is there a lawful something, structured precisely enough to start or bounce or persist at all? That question stands entirely upstream of the dynamics, untouched by whether the timeline has an edge. Third, the theory's own neatness betrays the claim. And here we harvest a seed planted in part 1. Loop quantum gravity does not float free of fine-tuning. It inherits it and adds to it. The Planck scale itself, the supposed bedrock, is built from 3 fundamental constants: the gravitational constant, the speed of light, and the quantum of action. A universe that permits structure, chemistry, and observers depends sensitively on the values those constants take. The theory presupposes that exquisite calibration. It does not explain it. And recall the Barbero-Imerzi parameter, gamma, the free number that had to be chosen, not derived, to make the black hole entropy come out right. The program's most celebrated point of contact with reality leans on a constant tuned by hand to fit the answer. That is the opposite of a theory that explains itself away. It is a theory that, at its proudest moment, reaches for a dial and sets it where the universe already insists it must be. What is the name for a structure this rigid, this law-laden, this precisely calibrated, that nonetheless cannot account for its own laws or constants? It is not the signature of a self-explaining accident. It is the fingerprint of a mind. And the final claim can be answered briefly, because the literature answers it for us. That consciousness is merely matter, since physics is fundamental and complete. But physics is not complete here, and its own best practitioners say so. There is no accepted physical theory of consciousness, not in loop quantum gravity, not anywhere. Roger Penrose, no friend of vague spiritualism, a mathematical physicist of the first rank, said plainly that to accommodate consciousness we will need, in his words, a major revolution in physics, that the science we have does not yet reach it. To use a theory of granular geometry to reduce the mind to matter is therefore to outrun the evidence by the length of an entire unsolved problem. The hard problem of consciousness is not closed by quantizing area. It is left exactly where it was, open, and pointing beyond the physical. There is a reply the confident skeptic will reach for at this point, and it deserves a direct answer because it is the load-bearing assumption beneath all four claims. The reply is, give physics time. We do not yet have the full theory, the skeptic says, but we are close. The dynamics will be tamed. The classical limit will be derived. The experiments will come. And when the dust settles, the granular, timeless universe will need no self, and no soul, and no God. It sounds like patience, like trust in science. But examine what it actually is. It is a promissory note written against discoveries that have not been made. Faith, in the precise sense, faith in a future that may or may not arrive. And it is faith held in the teeth of what the field says about itself right now. The literature does not whisper its limits, it announces them. The dynamics are unresolved. The semi-classical limit is not fully under Crow. The semi-classical limit is not fully under Crow. The semi-classical limit is not fully under Crow. The Dyer-Langber ridden a little. Then it a little dine, the sum of the dine. The dynamics are unresolved. The semi-classical limit is not fully under Crow. The relationship between the full theory and its cosmological models is debated. Direct experimental support is, in Rovelli's own flat phrase, lacking. And the theory, by his own admission, could very well turn out to be physically wrong. To take a candidate this provisional and hand it the keys to the deepest questions a person can ask, am I real? Am I one? Am I free? Is there a ground beneath the world? Is not the rigor of science. It is the overreach of a worldview wearing science as a costume. The honest scientist says, this is a beautiful, unfinished attempt, and we do not yet know if nature agrees. Everything past that sentence is philosophy, and it must argue for itself. And when it argues, it runs into something it cannot dislodge. The universal, unbroken testimony of every human life that there is one of you, persisting, not as a theory, but as the bedrock of every theory, the conviction present in every person, in every culture, in every age, that the one who woke this morning is the one who will sleep tonight, that there is a single I that remembers, intends, regrets, and hopes. This is not a fragile inference that a clever model can correct. It is among the most certain things a human being possesses, more certain than any equation, because every equation is something the I considers. When an innate, universal conviction this deep collides with an unconfirmed result in a simplified model, the rational response is not to surrender the conviction, it is to suspect the overextension. The burden of proof does not lie on the person who knows they are one self. It lies heavily on anyone who would talk them out of it, using mathematics that has never once been confirmed by an experiment. Look then at what loop quantum gravity actually shows when you strip away the costume. Because the bare physics is itself an argument the skeptic did not intend to make. This is a theory of staggering order. Geometry does not sprawl. It is quantized into precise, discrete spectra. Black hole entropy is not loosely correlated with size. It is chained exactly to area, in fixed units of the Planck length squared. The collapse of a universe does not wander. It is turned at a sharply defined critical density into a rebound. The whole structure is so constrained that even the location of the fundamental graph must be divided out as physically meaningless. Whatever this is, it is not the residue of chaos. It is law upon law upon law, calibrated with a precision the older arguments between order and disorder never dreamed of. The fine-tuning the program inherits, the constants it presupposes, the free parameter it must set by hand to match the entropy of a black hole. Every one of these is a place where the universe turns out to be not loose and accidental, but tight, specific, and mathematically exact. Precision of this kind is not the fingerprint of nothing. The deepest layer physics can presently imagine is not a formless void from which order somehow lurched. It is order itself, all the way down. And order is the kind of thing that has a source. This is the part that stays with me, and I return to it often, not because it is comfortable, but because it is hard to escape. The materialist set out to use the granularity of space to dissolve the self, and discovered that the granularity could not touch the one continuous thing, the awareness for whom the grains are a single world. The skeptic set out to use the timeless equation to abolish freedom and the creator, and ended up describing an eternal, lawful, ordered totality, which is the oldest picture of a creator there is. The physicist set out to make the universe self-explaining, and found a structure so law-laden and fine-tuned that the laws and the calibration cry out louder than before to be explained. At every turn, the attempt to remove the intelligent cause uncovered fresh evidence for one. What does it mean that the more deeply we look into the fabric of space, the more rigid and law-bound and precise it becomes, and the less able it is to account for the one who is looking? It means the trail does not end in the grains. It runs through them and out the other side, toward a mind. Let the cascades settle, because the four claims fall together, and each fall braces the next. The flickering self is a misreading. Granularity does not strobe you out of existence. And even if space is grains, the unified experiencer who knows them as one is the thing the grains cannot build. The timeless equation does not abolish agency. Relational time recovers becoming, and a truly timeless order points to a timeless cause rather than to no cause at all. The cosmic bounce does not remove the need for a creator. It relocates the question to the laws and constants the bounce presupposes, and it inherits the fine-tuning it claimed to escape. And consciousness remains unexplained by the explicit admission of the field. 4 extrapolations, each reaching past what the equations permit, each collapsing back when the hidden premise is exposed. And in every case, the physicists themselves are the first to mark the limit. Carlo Rovelli, reviewing his own life's work, wrote that direct or indirect experimental support is lacking, and that the theory could very well turn out to be physically wrong. That is the voice of the science. The voice that says these equations have abolished the soul is not the science. It is a worldview borrowing the prestige of a theory that has not yet earned a single experiment. So what does the evidence, followed honestly, actually point toward? Look at what loop quantum gravity is, taken at its best. It is a structure of breathtaking mathematical rigidity, geometry quantized into discrete spectra, entropy chained precisely to area, a critical density that turns collapse into rebound, a covariance so constrained that the location of the graph itself must be quotiented away. Whatever else it is not chaos. It is law upon law upon law, order of a depth and precision that the old debate never imagined. The question the evidence forces is no longer, is there order or disorder beneath the world? The order is not in doubt. The question is the one the loose claims cannot face. Why this rigid, mathematical, fine-tuned order at all? And who is the one continuous self for whom that ordered world appears as a single, seamless, living present? Unconscious quanta do not write laws, do not set constants, and do not wake up. The laws, the calibration, and the experiencing I are three things this magnificent theory describes around but cannot produce, and three effects that point past the entire physical order in the same direction are not three coincidences. They are a signpost toward an eternal, intelligent cause outside of time, the ground of the law and the constants and the conscious soul that perceives them. Let me bring this exploration to a close. We began with a headline, that you flicker out of existence trillions of times a second. And we followed it down into one of the most serious attempts physics has made to ask what space is made of. We met the spin networks that recast space as a web of discrete relationships, the area and volume operators with their countable spectra, the Planck scale where smoothness may give way to grain. We met the spin foams and the frozen equation in which time does not appear, and the cosmic bounce that turns the Big Bang into a big bounce. And then we examined and found at every turn that the precise and modest physics had a grand and loose claim hovering above it, waiting to be mistaken for it. The flicker is a misreading. The discreteness is spectral, not a strobe. The timeless equation does not freeze the heart. The bounce does not banish the cause. It inherits the fine-tuning and leans on a number set by hand. And the conscious self, the one who takes the granular world and knows it as one smooth life, is the single continuous thing in the whole account, the explanatory remainder that points beyond the geometry to the one who gave it. The smoothness of space may indeed be an appearance, but an appearance requires someone to whom it appears, and that someone was never made of quanta. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds. Space may be granular all the way down, a web of relationships with no smooth floor beneath. But the one who feels the floor as whole, who gathers the trillion grains into a single standing now and calls it my life, is not a flicker and not a fiction. You were never the smooth illusion. You are the one to whom it is shown. Sleep well tonight, resting on a fabric far stranger than it seems, held, like the laws that weave it, by something that does not itself come apart. Good night.